I was reading a bit on the internet about sore eyes, and one thing caught my attention, and that is to ensure that you spend some time each day, several hours, looking at distance, not like reading a book or a screen, but looking at greater lengths. So what I've decided to do is, I got up earlier this morning, and it's now early afternoon, and I'm filming, so that's good. So I'll keep getting up earlier till it's almost dawn. So I'll become like a peasant, Chinese peasant, who gets up at dawn, and I'll go to bed earlier than usual. And that way I can get into a routine. Then I can do all my board writing and filming and processing, particularly the processing, because that involves looking at a computer screen. I can do all that during the daylight, and in the afternoon, say mid-afternoon, I can go to my favourite park, because I'm retired. I'm an ARCer, A-R-C, after retired career. So I can get my long distance scene at the park, and I love green anyway. And I notice I have my best thoughts, my deepest thoughts in that environment with its lovely green. Whereas here when I'm working, thoughts tend to be somewhat superficial, and that's sort of normal. So that will probably become my routine from now on. So hopefully you will not see many evening filmings from now on. That's the plan anyway, until something else comes along, as it always does. Okay. This board, we will start describing the use. How do you actually use a PDA, a push-down automaton? So I'll give a sort of an informal description of our first example of the use of a PDA, and we'll use this particular language as the language we're trying to recognize. And then how many? So nearly 2 sessions. Three and a bit squares on the formal definition of a PDA. We've done formal definition before for finite automata, deterministic and non-deterministic. So that will be for quite a while, and after that we will do one full example of the use of a PDA, and begin on a second. And there are 3 in the text, examples of use of PDAs. And after that we will start doing theorems about the equivalence of non-deterministic PDAs and grammars, CF grammars, context-free grammars. Okay. All right. Well, let's start with our first example of the use of a PDA, and the task is to recognize this language. Now, I've seen it before. So we have a string of zeros, n of them, followed by a string of ones of equal number. So there are n and n. So we have n zeros followed by n ones, and n can vary, non-negative. So any string that has that form belongs to this language, and you're asked to design a PDA, push-down automaton. That's an automaton with a stack, basically, push-down, stack. I don't know why don't I just call it a stack automaton? Some of the labeling conventions I find rather silly. Alright, so how intuitively, I mean, imagine that you're the automaton. I have just realised I have not shut the sliding door, so I'll take a few seconds and do it. I won't stop the camera, but it'll cut the background noise. Now, do you notice things a bit quieter? Yeah. Alright. So imagine you're the PDA yourself. How would you go about detecting the strings of this language? And remember, now you've got a stack. You now have a stack. So you now have effectively infinite memory. So one approach is just read off all the zeros, and each time you read a zero, put it on the stack. Okay, just so read this bunch. So read the symbols for input. As you read a zero, push it onto the stack. Okay, so you've now got all these zeros on the stack. Now, when you see a 1, then pop a 0 off the stack. Okay, for each time you see a 1. Right. Now, if you finished your reading, okay, and the stack's empty of zeros, then accept the input. Does that seem intuitively obvious to you? Okay? Because every time you see a 1 now, you're popping a 0, and if your stack is now empty, when you've read your last symbol in the input string, well, then you know there must be an equal number of 1s and 0s, and therefore accept. Right? You accept that string. Okay, but there's lots of ways that can fail, that can go wrong, and in each of them, I think 3 different cases, I think, reject. Okay, so how can it go wrong? I mean, how many ways can you reject? What are the ways that you can reject? Okay, so here's one way. So it's sort of common sense. You just give it a little bit of thought. So if the stack goes empty, well, there's still 1s in your inputs. That hasn't been said here, but you still have 1s in your input stream. Okay, so reject. Why is that? Well, that means there are more 1s than 0s. Okay. How else? Now, wait a minute. Well, here's another way it can fail. So you've run out of 1s in your input stream. Okay, but the stack still contains 0s. Now that means that there were more 0s than 1s. Okay, so hence the numbers here are not equal. So reject. So that doesn't work. What else? Now another way is now notice all the 0s on the left and all the 1s are on the right. So if you have 0s reappearing after 1s, then reject, because then you'd have some 1s on this side, and that's not part of the language. They're strings that don't obey this definition. Okay, so 3. Now this is an informal